Good day and welcome. What we're going to talk about today is we're going to talk about the effect of friction forces. Now, we have avoided friction so far in our conversations, but now we'll get into the details on what friction is. And again, I refer you to lab number 7. In lab number 7, the first part, we get to do friction forces. So let's start off with our discussion here. Let's start off with a simple problem. If we have a box that has a force of 10.5 newtons to the right, and the box is moving with a constant velocity, then what is the magnitude and direction of the frictional force? Assuming here that the box has a mass of 5 kilograms, So all we have to do is we go ahead and draw the box, and we're going to apply a force of 10.5 newtons. And if this is moving with a constant velocity, then the net force has to be 0. So therefore, we must have an equal and opposite force here of 10.5 newtons pointing to the left. Okay, so we know our frictional force is 10.5 newtons to the left. In example number 2, the question is, the same cart is now pulled to the right with a force of 15 newtons. So since we're pulling to the right with 15 newtons, what's the frictional force and what's the acceleration? As you should have seen in lab number 7, the frictional forces does not change. The frictional force will remain the same as the box slides. So if the frictional force turns out to be 10.5 newtons, then the acceleration is going to depend upon the net force, which is F net equals ma. So that means we've got to take 15 newtons to the right, we subtract 10.5 newtons to the left, and we're going to divide the whole thing by the 5 kilograms, and we're going to end up with an acceleration of 0.90 meters per second squared. All right, but the key behind this is the frictional force doesn't change. What about if the cart is pulled to the right with a force of 10.5 newtons but doesn't move? What's the magnitude and direction of the frictional force? Again, because the acceleration is 0, in this case because the cart isn't moving to begin with, the box isn't moving to begin with, then you must have an equal and opposite force to the left, and so you have to have 10.5 newtons to the left. And then finally, if the cart just starts moving at 15 newtons, what is the frictional force just before it starts moving? And as we see, if the cart is not moving, the acceleration is 0, so whatever the force is to the right, you've got to have an equal force to the left to counter it. Therefore, the answer is going to be 15 newtons to the left. Now let's talk a little bit more about what the nature of the frictional force is, and I'm going to use as an example what happens when you move furniture. We've all had the experience of where we've had to move a bookcase on a carpet or something like that. And what we find is when we start pushing the bookcase, when we start giving that bookcase a push, it doesn't move, especially if there's a lot of stuff in it. When you start pushing it, it doesn't move. And if you push it harder, it still doesn't move. That means that there is a force that is opposing the force that you're pushing with. That frictional force has got to increase as you increase the force, as long as the cart does not move. We're going to keep pushing the bookcase. We're going to keep pushing the bookcase over and over and over. We're going to push it harder and harder and harder. We push the bookcase harder. At some point, and again, we all know this, we've done this, at some point the bookcase is going to start moving. When that happens, we discover something very nice. Namely, it takes less force to keep it moving than it does to get it moving. And the amount of force we need to keep it moving doesn't change no matter how fast we go. And so what we see, once the object is moving, it doesn't matter how hard we push the bookcase. It will keep moving, or it will have a frictional force that remains relatively constant. Because of that, there are two kinds of frictional force. The first kind of frictional force is going to occur when the bookcase is not moving, in which case we're going to call that static friction. Static meaning not moving. And then we're going to have a different kind of frictional force, which we're going to call kinetic friction, because that's the friction of the object as it moves. Another way of thinking about it is you can think about static friction like traction. That is to say, like when a tire grabs onto the road, the tire grips the road, that's actually static friction going on there. And then kinetic friction, well, that's what happens when the tire skids. And when that happens, the tire slips, so that the entire surface of the tire slips over the surface of the road. And so we'd find we don't get as much force, we don't get as much push from kinetic friction that we do from static friction. Okay, so let's take a look and let's see if we can figure out what is related to our kinetic friction, what's related to our static friction, what other forces are involved. So back to the bookcase. There we are pushing the bookcase. We're going to push the bookcase over to the right. What are the forces that are going to work on this bookcase? Well, doesn't take much to go through. We've all done that. We've all had this experience. Turns out that there are 4 forces that are working on the bookcase. We have the weight of the bookcase pulling downward caused by the pull due to gravity. We have the normal force, which is pushing upwards, which is caused by the surface of the rug interacting with the surface of the bookcase. We have the applied force that we're pushing over to the right. And because the bookcase is not moving, we're going to have static friction, which is pulling to the left, which is opposing the motion. Okay, so back to being college students earning money by moving bookcases around. Good question is, what can you do to reduce friction? There's essentially 3 things you can do. The first thing you could do, and which you should do, is take the books out of the bookcase. When you do that, that's going to reduce the weight of the bookcase. So as you can see, our weight force goes down. The vector gets smaller. But the normal force is also going to get smaller as well, because the normal responds, so to speak, to how hard it's being pushed down by the weight. So the question comes, what affects friction? Is it the weight or is it the normal force? Okay. So let's go ahead and examine it a little more. This time we'll put the books back in, and instead we're going to lift. We have found out through our own experiences that if we lift something up, we're not going to get as much friction. In fact, if you can lift the bookcase completely off of the rug, you're not going to get any friction because there's no contact anymore between the bookcase and the rug. So let's go ahead and lift. If we do that, the weight will not change. What does change, though, is the normal force, because the normal force plus whatever lift, whatever upward pull we put onto the bookcase, those 2 together are going to be equal to the weight. And experiments have shown that our frictional force turns out to be proportional to the normal force. As the normal force gets bigger, the frictional force gets bigger. As the normal force gets smaller, the frictional force will get smaller. Okay, one last thing we can do, we can change the surfaces. We could push that bookcase on the carpet, and it's going to have a certain amount of friction. But what if we replace, or if we put in sliders? That is to say, pieces of Teflon or pieces of felt. What that does is now the Teflon is sliding against the rug instead of the bookcase sliding against the rug. So different pairs of surfaces are going to have different frictions. They're going to be slipperier or stickier depending upon the types of surfaces. For example, if the bookcase had a surface made out of sandpaper and we had a rug made out of sandpaper, that would be very, very sticky. But if instead we had the bookcase made out of, say, Teflon and the rug was made out of ice, that's obviously a stretch, but then that would be a very, very slippery movement. Okay. So what do we end up getting? We have this proportionality between the kinetic friction force and the frictional and the normal force. And that makes sense because what friction is, it's how 2 objects are moving against each other parallel to the direction of motion. Let me give you an example. If I draw a picture of one surface, if we look down in the microscopic level, it's not going to be perfectly smooth. It's going to have some roughness to it. And the other object is going to have some roughness to it as well. I'm exaggerating the roughness. Let's say it's a different surface. Then what happens if I take these two objects and pull them in opposite directions like that? Then obviously the roughnesses are going to have to bump off of each other, bouncing up and down. The more I push downward on these two objects, if I push these two objects downward as well as pull them across, that's going to be tougher to do. That's like taking two pieces of sandpaper, pressing them against each other and trying to slide. Does not work. You have to hold them as loosely as possible. So, as I said before, this frictional force is proportional to the normal force, so we can write F sub k is proportional to N. What is the constant of proportionality? What is the number that we're going to multiply N by to get our frictional force? And that's going to depend upon the surfaces that we're applying. So we're going to call this number we multiply, we're going to call this coefficient the coefficient of kinetic friction, and we write it as the Greek letter mu sub k. Now mu sub k is going to be a unitless number, no units of measure attached to it. It's because we have newtons on the normal force and we have newtons on the frictional force. And so if we take newtons and multiply it by a number, we're going to get newtons back. Here's a place where a lot of students make a mistake. You look at mu k and you think that's friction. Mu k is not friction. Mu k is the coefficient of friction. F sub k is the magnitude of the frictional force. Okay? So mu k is going to depend upon the surfaces. There's a table of coefficients of friction in your textbook. F, however, depends upon the surfaces and the normal force. The bigger the normal force, the bigger the friction. The smaller the normal force, the smaller the friction. Okay? So when you do your problems, do not mix up mu k with F sub k. One thing you can do though, is when you replace your, when you're solving your problems and you have F sub k, you can replace that with the expression mu sub k times n. And I'll show you how that comes into play later on. Now, what about static friction? Static friction is similar, but it's a little bit different as well. Namely, static friction is the attraction between the atoms of two different objects. Again, we're going to have the two surfaces. So there's this surface here. Here's the rough surface here. But this time, the object's not moving. And so what we have is a molecule here and another molecule here. There's going to be a bond in between. This molecule here and this molecule here, there's going to be a bond in between. So what we have to do is when we start moving the surfaces, when we start pulling them apart, we have to break these bonds. And that requires more force than just getting the objects sliding against each other. Once the objects stop moving, then the bonds can reestablish, and then we need more force to get it going. The static friction is more often than not stronger than kinetic friction. Again, we've added this additional intermolecular bonds here. Okay? It will vary with the applied force. You push it a little bit, the static friction is going to get bigger, but it doesn't necessarily mean it's going to start moving. If you push it harder, the static friction continues to get bigger. Eventually, you're going to get to a point where there's a maximum static friction. At this point, we're going to go ahead and say this maximum static friction is going to be proportional to the normal force. Again, we see the same effect. If we increase the normal force, either by adding weight to an object or pushing down on an object, we're going to increase the static friction. Again, that's like taking two pieces of sandpaper and pressing them into each other. The friction is going to increase. Because it varies with the applied force, we're going to write an inequality this time that F sub s is less than or equal to mu sub s times n. So when F sub s is equal to the coefficient of static friction times the normal force, that's the maximum static friction. No more static friction can be applied. Okay, so let's try a simple problem here. If we have a cart that starts moving at 15 newtons, what is the coefficient of static friction? The box has a mass of 0.5 kilogram. It's a horizontal surface with no other forces. okay? So that's our problem. I'm asking what the coefficient of static friction is because this is similar to example number 4. When the cart is just about to start to move, we're going to take the measurement then. So where do we start off? We start off with a cart looking like this, and let's take a look at our free body diagram. We have the weight pulling downward. We have the normal force pushing upward. We have the applied force, which we're going to call F, pulling to the right. And we're going to have static friction pulling to the left. Now, in this particular case, what we see is because the acceleration is 0, the static friction has to be equal to the applied force, and the normal force has to equal the weight. Okay? So the normal is equal to the weight, so let's replace that with a mathematical expression. That means normal N is equal to m times a sub g, mass times the free fall acceleration. How do we find the static friction? Static friction is equal to mu s times n. In this case, we're looking at the maximum static friction, so we're going to make it an equality. So F sub s equals mu s times n. From our previous equation, we see that n is equal to mass times the free fall acceleration, so we'll just do a straight substitution. And that gives us the expression that F sub s, the static friction, is equal to mu sub s times m times a sub g. We know what the static friction is. That's just going to be the force we apply. And we can calculate the weight by taking the mass, 5 kilograms, and multiplying it by 9.8 meters per second squared. And that gives us a coefficient of static friction of 0.306. Again, 3 significant figures because we have trailing zeros in the problem. Okay, so that's the first problem. Let's try example number 5. Here it gets a little bit more interesting. We have a block with a mass of 2.75 kilograms at rest on a ramp. The angle of the slope is slowly increased and the block starts moving when the ramp is at 22.5 degrees. What is the coefficient of static friction? Right, we've got ourselves a little bit more complicated problem, so let's go ahead and draw the picture, and there's the picture of the block sitting on the ramp. We know the numbers that we're given is that the mass is 2.75 kilograms, that the angle of the slope is 22.5 degrees, that the velocity is 0 because we're looking at the moment just before it starts sliding, but we do not know what the coefficient of static friction is. So the next step, if we're dealing with 0 velocity, we're dealing with forces, we're dealing with an acceleration, is we're going to have to deal with Newton's second law. That means we have to go with a free body diagram. So here's our free body diagram. Let's identify all of the forces. We have the weight, which is pulling straight down. And we can calculate the magnitude of the weight by taking the mass of the block and multiplying it by the free fall acceleration. So W is equal to ma sub g. Okay, what else do we have? We have a normal force. We can't calculate the normal force, not directly anyway, so we're going to have the arrow of the normal force pointing perpendicular to the ramp. We also have static friction, which is essentially holding the block in place. Static friction is pointing upslope. We don't know the magnitude of that, but we can calculate it because we have an expression that says the maximum static friction, F sub s, is going to be equal to mu sub s times n. All right, so we have our three forces. We know the acceleration is 0, so let's go ahead and write the vector equation of Newton's second law, which gives us F sub s plus n plus w equals 0. The next step, well, whenever we write the vector equation, we usually follow it up with a component equation. So I'm going to replace each of those vectors with a column of components. And if we look, we see F, so we have we replace F with Fsx and Fsy. We have normal with Nx and Ny, and weight with Wx and Wy. Now we have to come up with the expressions that give us those particular components. To do that, we're going to do our trick of rotating the coordinate axes. Now, if you can't remember, not a problem, here's how it works. Our standard coordinate axes orientation is to the right and upward. X is to the right, and y is up. But if I rotate those coordinate axes so that the x-axis is parallel to the slope, then the y-axis becomes perpendicular to the slope, and so the angle that I have to rotate turns out to be the angle alpha. Now, by doing this, we see that our frictional force is going to have strictly an x component, and our normal force is going to have strictly a y component. We now have to find the components of our weight, and so we just draw the parallel and the perpendicular components. The component that is perpendicular to the y-axis, the component that is perpendicular to the surface, that points down towards the y-axis. And the component that is parallel to the surface, well, that goes parallel, down slope. So we write those as wy and wx. And the angle alpha turns out to be this angle right here. So now comes the next question, which is, what are the expressions for wy and wx? Well, since alpha is our angle, wy is adjacent, so we're going to use a cosine, and wx is opposite the angle alpha. And so that gives us the expression wx equals mag sine alpha, and wy equals mag cosine alpha. All right, where do we go with that? Well, now we can go ahead. We have the expressions for each of our components. For f, we replace that with minus mu s times n. And that's because it's minus sign because it's going upslope, and we've said downslope is positive. For our normal force, we replace that with 0 and n. And for our weight components, we replace that with positive m a sub g sine alpha and minus m a sub g cosine alpha. Those are our x and y components respectively. And again, if the normal force is pointing in the positive direction, then the y component of the weight has to be pointing in the negative direction. Next, that gives us our two equations. Our two equations become mu s times n equals mag sine alpha, and n equals mag cosine alpha. That essentially, we now have two equations with two unknowns, but the good news is we really don't need the normal force. So let's go ahead and take that expression for the normal force in the second equation, plug that into the variable for the first equation, and that gives us mu s mag cosine alpha equals mag sine alpha. And here a miracle happens. The miracle being that the weight cancels. So mag is on both sides of the equal sign. In addition, there's one more thing we can take advantage of. There's a trig identity that you may remember, that if I take the sine of an angle and divide it by the cosine of the angle, that's going to give me the tangent of the angle. And so my final expression turns out to be mu s equals tan alpha. So I don't care about the block. I don't care about the mass of the block. I don't care about the speed of the block. I don't care anything about that. All I care about is what is the angle at which the block starts to move. And that gives us a coefficient of static friction for this particular experiment as 0.414. Yay, fantastic. Okay, and that's, by the way, that's another reason why I keep saying, please do your algebra first. Because if you had plugged in numbers because you know m, a, and the angles, then you would have ended up with a bunch of numbers, and you still would have gotten the right answer, but you would not have seen this expression right here. You would not have seen that mu s is equal to the tangent of the angle. Why is that important? That means I don't have to recalculate things all the time. I don't need to take the weight of the cart all the time. All I need to do is put the cart on the slope, tilt the slope up until it lets go, and then calculate the coefficient of static friction using the angle, using the equation that we've just derived. Let's do one more example. And this is not one I discussed in class, but it's kind of interesting. A hockey puck is sliding on the ice. It goes 120 meters from an initial speed of 20 meters per second coming to a stop. What is the coefficient of kinetic friction between the ice and the puck? Now, looking at that, you go, wait a minute, how can I figure that out because I don't know the mass of the hockey puck? The answer is you don't need to. Let's go ahead and go through our steps again. First, we're going to draw a picture. And when we draw the picture, what we get is the hockey puck starting here at some initial point. It's going to have a velocity, an initial velocity going in that direction. It's going to get to this point right here, in which case the velocity is now equal to 0, which means there has to be an acceleration in the opposite direction. So we know that it's going to have an acceleration. The next thing is, what are the forces acting on the hockey puck? Well, we know we've got weight pulling downward. We have the normal force pushing upward. And we're going to have kinetic friction, which is going to cause it to slow down. And notice, when we look at the forces and we see how the forces balance out, we see that the net force is pointing to the left. That's the direction of the acceleration because the puck is slowing down. So we can then write our vector equation, W plus N plus F sub K equals MA. Okay, let's go on to the next step. Let's replace them with components. When we replace them with components, we see that the weight is strictly in the negative y direction, the normal is in the positive y direction, and the friction force is in the negative x direction, and we're going to let the acceleration be in the negative x direction as well. This is assuming that positive x is in the direction of the puck's motion. All right, that gives us our two equations. The first equation is mu k times n equals ma. Can't solve that because we don't know the normal force and we don't know the mass and we don't know the acceleration. The second equation turns out to be that the weight is equal to the normal force. That is true in this particular case. So mag equals n. We go ahead and substitute that into the first equation and we get mu k m a sub g equals m times a. And now we see we don't need the mass of the hockey puck. The mass cancels out, and we get mu k is equal to a over a sub g. Now, the only thing we need to know now is, how do we find the acceleration? Well, let's make our table. Since it's a constant acceleration problem, we make our table of variables. We get delta x, v0, v, a, and t. We are given delta x is 120 meters. We're given the initial velocity. We know the final velocity is 0. So from that, we can find the acceleration by using v squared equals v0 squared plus 2a delta x. And we end up using the negative root to find the acceleration because the acceleration is pointing in the negative direction. With that, we find the acceleration of the puck, and that will solve the problem. And so that's just a little reminder that the coefficient of friction is pronounced mu, so just think of what the physics cat would say. All right, thank you very much, and I will see you next time in class.